Good evening, everybody.
Good evening.
This evening we're welcoming Dr. Chris Arridge, who is a reader in Planetary Physics at Lancaster University. His work focuses on the giant planets and involves both data analysis and computational simulations. He was a member of the Cassini magnetometer and plasma spectrometer teams and is a co-investigator in the magnetometer team for the JUICE mission, to be launched in the next few years to Jupiter. He's also an amateur dancer. Well, we'll have to have a demonstration later, I think. And a trainee counsellor and psychotherapist. So can we please, in a warm Mexborough and Swinton way, welcome Chris Arridge.
I've been doing this talk for a while now, and I really enjoy giving this talk because one of the things about the work I do is that we think a lot about how the measurements were made. You know, we often send a spacecraft off to a planet and we get data back. You know, and then we use that to find out things about planets and, you know, what rocks are made of and all that sort of stuff. But I like this because it thinks a bit more about the how of that. How are those measurements made? How do they get back here? How does the spacecraft get there? And all of that sort of jazz. So that's what this talk is about. One of the first things I'd like to do, just to I guess just to make it concrete what I'm talking about, I'm going to use the word spacecraft a lot in this talk, and when I use the word spacecraft, I obviously don't mean this. And so I'm talking about robotic space exploration. So I'm talking about things that don't have humans on board, and I'm talking about spacecraft that are, let's say, the size of a minibus or smaller, size of a sort of a 15-seater, 12-seater minibus or smaller. Some even, you know, some are a lot smaller than that, some more like coffee table size. So that's what I'm talking about when I talk about spacecraft. And the other thing that I think is, and I've started talking about this a little bit more in recent years, is that when we see pictures of space, we could easily be fooled into thinking that's an artist's impression. You know, you see something on telly, and it's getting hard now to tell whether it's a real photograph or something or fake. And I think that contrasts a little bit with stuff in the natural world, where you see pictures of plants and animals and stuff, and you don't immediately wonder, is that CG? So I'm drawing quite a distinction here, because and especially since some of the pictures that I show are almost so fantastical that they could be CG. So what I'm going to do is I'm going to put a little V on the slide when this is an actual visualization, a computer visualization, rather than an actual picture that a camera has taken on a spacecraft, and especially pulling it a little bit further back, that someone has built in a lab, in an engineering lab. Someone's designed it, built it, tested it, put it in a box, shipped it off to another facility for it to be bolted onto a spacecraft. So I like to make those points. I think it may be a bit silly, but I think those points are important to make. And the other thing to say is about the why of it. You know, so we can. I do believe that there is an aspect to this of saying that it's pushing the human frontier, and so, you know, we send things out to other planets because it's part of our natural human drive to explore, and but there is and then to also then do the science, to pose scientific questions and try and answer them. But I think there's also another human aspect to this, and that's actually looking back at our own planet. You go out to space not just to keep looking out, but also to take a reflective look in. So I show this picture because this was a picture released. Well, this was a picture taken by the crew of Apollo 17 in December 1972. It wasn't the first color picture of the Earth. This picture is known as the Blue Marble, if you didn't know. And it's a very famous picture. It's one of the most reproduced pictures from space in history. But it's sometimes described as the first color picture of the Earth, but it's not. The first color picture of the Earth from a satellite was taken in '67. But this has got particular resonance because it was released in the early 70s, when there was a lot of reawakening about the environment and the climate, and what we were doing to Earth. And so you know, this picture has sort of become synonymous with the Earth as a fragile place that requires care. And it's also interesting to note that this was actually the last time. This was taken when the crew of Apollo 17 had just done their burn to take them onto lunar injection, and this was the last time that a human being could take this picture manually with a camera. We haven't been in a position in space. A human being hasn't been in a position in space to take a photograph of this nature ever since Apollo 17, ever since 1972. So there's a reflective part looking down, but also we can keep looking outwards. And one of the and answering these questions, asking these questions, these science questions, and trying to answer them. So one of the things that we really want to do is we want to try and understand how the solar system came into being. It's one of the big questions that we want to try and understand. Where did we come from? And so one of the things we try and do is to try and figure out, well, you know, we've got this thing happened 4.5 billion years ago, 5 billion years ago when the solar system formed. What happened then? What was the physics, the science that was going on at the time that caused the planets to form in the way that they did? So this is a sketch of artist's impression showing a phase of solar system formation. We can see a cloud of gas and dust that's steadily being blown away from the sun, revealing the formed planets in its wake. And the idea there is if we can go to a planet and take some measurements, we can look at, say, a planet's atmosphere, look beneath the clouds as well to figure out the composition of the planets. That what they're made of gives us fingerprints to understand where they actually formed in the solar system, and thereby gives us some understanding of, well, how the whole solar system formed in the first place. You know, so the picture on the left is you know, some of the earliest pictures taken in situ of Jupiter. This picture on the movie on the left. We're obviously looking at the Great Red Spot here. We're seeing little black spots appear here and there up near the equator of Jupiter, and there we're seeing shadows cast by the Galilean satellites. And this sequence of images was taken by Voyager 1 just before my first birthday in 1979. I think this is a fantastic sequence of images, even though it's just in black and white. I think it's fantastic. And you can really see lots of detail there in how the atmosphere is behaving. And indeed, that's another science question we can ask. How do the atmospheres of other planets work? And then another thing that's, I think, perhaps becoming more and more interesting is how do all of these tiny worlds that orbit the giant planets behave? You know, so this is a picture of Io, some pictures of Io, the innermost of the Galilean satellites. We can see here in this video clip here from New Horizons, as it flew past Jupiter in 2007, on its way to Pluto, we can see this active volcanic eruption just off the limb here. And we can see this, if we look in infrared, we can see the bright infrared emission from all the heat released during this volcanic eruption. And as well, in the infrared, we can see all these little spots here that are lakes of lava on the surface of Io. You know, and Io is the first place away from planet Earth where we saw an active volcanic eruption. We've seen lots of extinct volcanoes on other worlds, but this was the first place in the solar system where we saw a volcano erupting. But, you know, this is just the innermost of the Galilean satellites, and some of the others are terribly different. You know, we go to Europa, and what we see here is a big ice ball, and I remember this being described as a big ball of frozen ice in the 80s, just after Voyager. But then Galileo came along and looked beneath the ice and found evidence of an ocean, a subsurface liquid water ocean underneath the ice. And so that's got plenty of people very excited about what we would find under that ice. And so this drives like a future goal of robotic exploration, is to get onto Europa or another similar ice world and somehow penetrate through the ice shell to get down into the liquid ocean underneath the ice. And what would we find under there? And people are particularly excited about finding something like this. And this is a black smoker from the Earth's oceans. The Earth's ocean's crust, where we have these hot volcanic gases emerging up into the ocean. And these sites on the Earth's oceans are teeming with life. So that's why this sort of thing is particularly interesting for planetary scientists. So there's lots of different bits of motivation here. So let's actually go and look at the actual process of doing this. And I want to start with, this is sort of like a bit of a history lesson, really. And what I'm starting with here is the launch of Mariner 2 in 1962. This is a photograph of the launch vehicle just clearing the tower. And Mariner 2 was launched in August 1962 and is the first spacecraft to fly past another planet, make a successful flyby of another planet. And you might ask, well, what happened to Mariner 1? Mariner 1 actually failed on launch and it blew up after launch. So this was the Mariner 2 was the first successful launch. And this is what it looks like. This is an artist's impression, a drawing of what that spacecraft looked like. It was launched in August of 62 and it had its closest approach with Venus in December of 1962, on the 14th of December 1962. To give you a sense of scale here, and also to label some of the bits and pieces that are on here, this box here, this box contains the electronics for the electrical systems for the spacecraft. The dimensions of this is about a meter across, about 3 foot across. These solar arrays here are about 2 meters long by about ½ meter wide. So what's that, about 15 inches wide, let's say, and 6 foot and a bit long. We have got this other structure here. We have got a pressure tank here, this spherical object here. And then this thing up here that looks a bit like a dream catcher, that's the antenna for the spacecraft to communicate with Earth. Those solar arrays there are producing electricity, obviously, to power the rest of the systems on the spacecraft. And there's a battery also when the spacecraft solar panels are not facing the sun. These solar panels are not articulated. The whole spacecraft, in order to get power from the sun, if you pretend you're the sun, the whole spacecraft needs to rotate itself around so its antenna solar arrays are pointing at the sun. And if it's not doing that, then the battery needs to pick up the slack. This antenna here, so this, we're in the realm of deep space now, and this antenna needs to communicate with an antenna on the Earth. And to do that, that radio transmitter that's as part of this radio system here, that transmits with a power of 3 watts. So if we think about other transmitters, the transmitter in my mobile phone is using about 1 watt to communicate with a cell base station, maybe a few miles away. But this antenna here has got to communicate over millions of miles in order to get the data back to Earth. And it does that by forming this into that big dish here. This is a parabolic antenna to focus the radio waves in one direction. So they just go to Earth, they don't go out in all directions. Now, something happened to Mariner 2 on its way to Venus, on its way to its closest approach with Venus, and we still don't know to this day actually what happened to Mariner 2. What happened was on the 8th of September, suddenly Mariner 2 didn't know where the sun was. It had a number of sensors on it that looked for bright things in the sky. It particularly looked for the sun, and then it looked for a fixed star, a particular star in the southern hemisphere. And if it knew where those two things were in the sky, then it could orientate itself in space, and it knew where to point its solar arrays so that they could receive power from the sun. But something happened where it suddenly stopped knowing where the sun was. And so something had actually come in and caused the spacecraft to stop tumbling. And so these spacecraft are so far from home that they can't simply just say, what do I do? Fix me. They've got to be able to get themselves in a safe position, into a safe state, and then call home to say, what do I do now? And so what Mariner 2 did is it stopped its tumble, and then it started to go in a scanning pattern, basically turning itself around so it could find the sun and it could find this reference star. And so once it had done that, it knew where to turn itself around so it could face its solar arrays to the sun so that it could receive energy. It was then in a safe position and then it could turn its antenna towards the Earth and say, hey, this has happened. I've turned everything off because I don't want to use any more power than I need to. What do I do now? And so some people think that it's actually struck by a micrometeoroid that caused it to tumble. We don't really know. The point is that this, even in 1962, the electronics were clever enough to be able to manage the situation. So let's go a little bit. Let's go forward to Mariner 4. So Mariner 3 was actually scheduled to go to Mars, but it was actually Mariner 4 that made it. You might ask what happened to Mariner 3, and based on what happened to Mariner 1, I think you know the answer to that. It blew up. This was a bit of a risky phase of solar system exploration. But Mariner 4 was going out to Mars, and it was launched in November of '64, and it had its closest approach with Mars on the 14th and 15th of July, 1965. It was, you can start to see some of the same bits and pieces. We've got this octagonal box that holds the electronics. We've got a pseudo parabolic dish to communicate with the Earth. This had cameras on board. It wanted to take pictures of the Martian surface. But the communications, the rate at which the data could come back from Mariner 4 were, I believe it was about 30 bits per second. You know, so we compare that with what with our broadband is doing at home, or even what we were talking about retro computing before we started, and we think about what a modem could do in the 80s. You know, so this is extremely low data rates, and you want to get a picture back. And it couldn't communicate that back quick enough. So what they did is they wanted to store the TV pictures, the photographs on board, and then transmit them at a slower rate after the flyby. So, you know, the technology you use in the 1960s was obviously tape. And so they built a tape deck. This is the inside of that tape deck. Here you can see the drum, and these are the winds around the wheels here. There's the tape head. And so for anyone who grew up in the 80s with pencils and C60 cassettes trying to get the tape back in the housing, the idea of building a tape deck and flying it in space fills me with dread. But they built it and it worked, and we got the pictures back from Mars. And this is what it looks like. And compared to a lot of modern pictures, it looks really rubbish. What you're looking at here is you're looking at Mars here. This is the limb of Mars, and this is space. As groundbreaking as this image was, it was taking so long for the computers of the time to process this photograph so they could produce this image and release it to the press, that the press started getting antsy, and they wanted to see pictures sooner. And so what they actually did was they printed out this. They printed out all of the pixels on the picture, so all of the numbers that make up each pixel that tell you how bright it is. They printed it out on massive sheets of paper, and then someone ran down to an art shop and bought some pastels, and then they said, well, wherever a pixel has a number between 45 and 50, we're going to make that brown, and so on all the way through to yellow for numbers 20 to 25. And then they basically sat there, colored in, did paint by numbers on this big printout, stuck it together, and that was the first TV picture that we saw, that human eyes saw from Mars. But as soon as the engineers, as soon as the top brass figured out what the engineers were doing, they tried to hush it up. It's like, you know, stay there. Don't show the press what you're doing. We can't be revealed to the world as doing a paint by numbers. But the press thought this was amazing, and that's actually ended up how this picture was first shown to the press, through this paint by numbers. And so now this picture now hangs in the hall at NASA's Jet Propulsion Laboratory, and this is the framed version as it was shown to the press. So I think that's an amazing feat of engineering, but also a feat of ingenuity, to think, well, how can we look at this sooner than the computers at the time is going to be able to do it. So that was Mariner 4. So we're just talking flybys here. We haven't put anything onto another planet, or at least NASA had not put anything onto another planet. And the first time they did this was in 1970, in the 1970s. And one of these was the Viking series of landers. So this is a photograph taken by Viking II in September of 1976. We're getting pictures in color now. And the thing with color is that you need to know if the colors that are being reproduced back on the ground when the pictures come back to Earth are the same as the colors there. You know, is red really red? What does red mean in that landscape? And so what they do is that they put this little swatch that I hope you can see I'm outlining here. They put this little color swatch in the field of view of the camera. You can see a couple of them here. They put these color swatches in so they know that if they see something that's got a particular color over here in this landscape, in this rock field, if they see something that looks red there, they can compare it with the red that someone painted on the spacecraft, and therefore they know how to calibrate the picture, how to calibrate the colors in the picture so they get something that's as faithful as possible to what it would look like to a human eye. So this was, you know, literally coming down to rest on Mars on rockets. But NASA started to get into a phase where they wanted to do things faster and cheaper. So they thought, well, why not just dispose of the rockets altogether and let's just make it crash? And so that's what Pathfinder was all about. So some of you may remember Pathfinder from the 90s. And what they decided to do was put the spacecraft inside of a whole load of inflatable bags. And as soon as the spacecraft had slowed itself down enough in the atmosphere of Mars, you'd release a heat shield. You basically you pop a valve, and it inflates all of these bags all the way around the spacecraft. Basically, turns the spacecraft to a massive bouncing ball with the spacecraft in the middle. It comes down to land. It bounces around on the surface of Mars, rolls around. As soon as it's come to rest, you deflate the bags, unzip, and your spacecraft comes out. And that was Mars Pathfinder. This is it being tested in the Mars yard in 1996. And then it reached Mars and took these pictures. So this should scroll if I've set this up right. It's not going to do it for me. What you can see here is a little rover that went with Pathfinder. This is known as the Sojourner rover, and this was about the size of a shoebox, and it just drove around on Mars and took measurements directly up against these rocks. You can see its tracks here through the Martian soil. You can see these bags, the landing bags here. You can see the solar arrays here for the lander. Any of you who have seen The Martian, the film The Martian with Matt Damon, this is the thing he goes and digs up so that he can talk to NASA again. So this was a real mission and a real spacecraft. And we've been doing Mars ever since. It's a real thing in our imagination, in human imagination. It's also a really interesting scientific target. And one of the big things there is water. And we see lots of evidence in these photographs from the surface of Mars for water having flowed on Mars at some point in its past. So we see all of these channels crisscrossing here, moving through these craters. So we've got good evidence that water has flowed on Mars at some point in the past, but the question is, where is it? Has it disappeared off into space? Has it gone underground? And so one of the things that they wanted to do was to try and look underneath the ground to see if it was there. And this is one of the experiments they did with one of the Mars exploration rovers to basically get one of its wheels and to use it a bit like a dog scratching at the earth to sort of scoop away at the soil to see what was underneath. And they actually did see evidence of some sort of ice. It's not clear if this was frozen carbon dioxide or if it was frozen water, but it sublimated quite quickly after it had excavated this little trench. So there's certainly something underneath the Martian soil, underneath that regolith. And one of the other things that you can do when you're on Mars is you can start to take pictures of sunsets. And whilst this looks like something from Star Wars, we are actually looking at sunset on Mars. So we're actually seeing the sunset. And apart from being quite an evocative picture to take, it also has scientific value, because as the angle between an observer and the sun changes, you're seeing different parts of the sky. The sunlight is going through different angles in the sky, and it affects the. We can see the changes in how the light is being scattered by the atmosphere. That can tell us about things like how much dust is in the atmosphere, how much water vapor is in the atmosphere. So it's got a scientific diagnostic value as well. And so if you haven't seen some of these pictures of these sunsets, I would recommend looking at them. I find them really, really fascinating and fantastic. And then, of course, we've got more advanced missions, and we've had a new rover land on Mars recently. This is a photograph from Curiosity, the Mars Curiosity rover that landed on Mars a few years ago now. But let's look at. I want to show you a movie of the actual landing, and I think this is fantastic. So this was a return to using rockets, and the idea is this: is you want to be able to do science operations straight away when you land. And so what they designed was this rig called the Sky Crane up here. The spacecraft was stowed underneath here, and then this whole thing hovered down towards the surface of Mars on its rockets, firing its rockets, and then it winched Curiosity down to the ground. As soon as Curiosity was on the ground, you cut the cables, this rig then flies off and crashes, and then Curiosity is ready to roll and do science. And there's a picture, it's a movie I want to show you here of the actual landing. You may have seen this, but I think it's fantastic. So what we're looking at is, this is a camera pointing from Curiosity down to the ground. So that thing that's fallen away, that's the heat shield. That's the heat shield that protected Curiosity and the Sky Crane from being burned up during entry into the atmosphere. So that's detached now. Once it's slowed down, that detaches off. We've got a parachute up top, and Curiosity and Sky Crane are just so coming down on their parachute, slowly coming down towards the ground on Mars. And of course, there are pictures of the landing sites from orbit, where you can see these various bits and pieces. You can see where the heat shield landed. You can see where the Sky Crane went off and crashed, and so on. But I found these images absolutely amazing. Actually seeing, like you would get from doing a skydive, you're coming down to the earth and you start to see things get bigger and bigger and get particular perspective of the landscape. So we see all of these features on the surface of Mars. This is obviously Gale crater where Curiosity landed. So we're seeing all of these features on the surface of Mars. And if any of you have done a skydive, you might know that it feels like you're hovering above the landscape for ages, and then suddenly the ground appears. And it feels a little bit like this here. So what's happening now is the parachute's being released, and it's now hovering down on its rockets. You'll start to see the rockets blasting away at the sand on the surface of Mars. And there we are. So there's almost first-hand footage of a landing on Mars, with the scorch marks from the rocket exhaust, showing you the action of landing. So I think that's an absolutely amazing piece of footage, showing us arriving on another world. I'm sure many of you have seen lots of those pictures from Curiosity, and I can't get enough of looking at them. They're all amazing. All through that process of Curiosity coming down to land, it was talking back to mission control, saying what was happening. And this is common all the way back to Mariner 2, and even to Sputnik. I'm sure you've all heard at some point the beep beep from Sputnik. And actually, that beep beep from Sputnik was carrying some information. It's carrying some information about the temperature inside Sputnik, inside the internal environment of that sphere. So the song that it plays back to Earth is encoded with information, and it sounds just like a modem. So I'm going to play you a little bit of actually what was being transmitted by Curiosity during that landing as it was coming down to Earth. I won't play it forever because it does sort of play on your ears a little bit, but I want you just to hear that sound. So all of those little changes in turn and phase they're all the carrier signal being changed by the pieces of information that Curiosity is transmitting. And just like with any other communications technology, there's extra information packed in there so that the engineers can detect errors in that data stream. Just like it's on the CD.
Because it didn't come through very well.
Oh, I can play it again, of course, yes. I can also provide it I can provide a link to it, but I'll play it again. See.
Thank you. That was much better.
That was better. That's good. It's a bit of an awkward. It's a very unpredictable and unpredictable sound to broadcast over something like this. But I can certainly point you in the right direction. So if you're interested in those sorts of sounds, there are websites where people have put different sound files of spacecraft talking back to Earth. And I think it's really interesting. And a bit strange if you've never sat and heard a modem connecting to a service before. So I would be really amiss if I didn't mention other space agencies. And so the Soviets, were launching stuff in parallel with NASA. And some missions particularly they were focused on were the Soviet Venera missions in the 60s all the way up to the 80s. And so Venera is Russian for Venus. And they had a number of firsts. So they were flying missions or trying to fly missions to Venus from 61 onwards. And they had some number of firsts. So Venera 3, that was a first crash landing of a spacecraft on another planet. So that was a crash landing on Venus. Venera 4, that was the first atmospheric entry of another planet. That was in 1967. And Venera 5, that was first soft landing on another planet. That was in December of 1970, so a few years before NASA did that soft landing with Viking on the surface of Mars. And so you can see some of what these Venera spacecraft look like. They've got a lot of the similar sorts of elements. We've got a parabolic antenna here for communication to the Earth. We've got solar arrays here. Lots of the same sorts of equipment. This part up here, this is a lander, atmospheric entry lander. So there's lots of the same sorts of elements. And so we've returned pictures. The Soviet missions returned pictures from the surface of Venus. We see this volcanic landscape here. We can see these pictures from Venera 13 on the surface in 1982. These have been reprocessed here by Don Mitchell in recent years from the original raw files from Venera. And I think it's really important to think about what an engineering achievement that is. I think I've got a picture from Venera 14. Yes, this is from Venera 14 on the surface of Venus. So the next one, the next mission. And there's the same sort of thing. These color swatches that you can see here. The pressure and the temperature on the surface of Venus are so intense that it affects how the color comes through on the camera. And so this is actually the colors that is painted, but the actual effect of temperature and pressure changes in the atmosphere and means that this is actually what they look like, those colors look like. So again, that's a real example of how you need to do that color balancing, that color correction. But I think Venera 14, this spacecraft landed in 1982, and it lasted on the surface for 57 minutes. So it flew all the way from Earth to Venus, landed, got through the atmosphere, landed on the surface, and then it only stayed there for 57 minutes before it was destroyed. Which is, it doesn't sound long, but when you think that it was only engineered to last 32 minutes, that's quite an achievement. And it was struggling. It was on the surface. They're struggling in a temperature of 465 degrees C, and in a pressure of 94 Earth atmospheres. So that's just an incredible achievement to be able to engineer something to survive in that environment. And to put that into a bit of context, 94 atmospheres is the equivalent of being about 940 meters below the surface of the ocean. That's out of reach of most military submarines. So it's operating in an extremely harsh environment, and that's, even think of that as a challenge nowadays, let alone in the early 80s. Venus has continued to be an interesting place to go. We see lots of evidence of extinct volcanoes. There's some idea that some of this volcanism might not be all extinct, but because of this thick atmosphere, and particularly the intense greenhouse effect, it shrouds the surface from orbit. You just can't get through to look at the ground. And so one of the ways that was used to get through is to use something called synthetic aperture radar. So use radar basically to map the surface. And this was done in the 80s, and particularly by a spacecraft called Magellan. This is Magellan here. If that antenna looks familiar to you, then I wouldn't be, I'm not surprised, because it reused parts of Voyager, which I'll talk about shortly. Yeah, so the Magellan maps the surface of Venus in exquisite detail, and it's the best that we've done so far, and people are now trying to go back and improve on what Magellan did. So this is bringing us right up into sort of the mid-80s, and I've skirted through some of the exciting stuff that happened in the early 70s, and I've focused really on the inner solar system. So let's look further afield. So in 1964, there's a chap called Gary Flandreau who was basically doing an internship at the California Institute of Technology, Caltech, and at JPL. And he basically noticed that in the 70s, Jupiter, Saturn, Uranus, and Neptune were sort of roughly lined up. And he realized that actually you could visit all four planets with one spacecraft. And this discovery and the analysis, the technical analysis of what he did, basically evolved into the Voyager missions to the giant planets. And so there were two spacecraft built. They're essentially identical, except one has a little bit more radiation shielding because it went a bit closer to into Jupiter's radiation belts than the other one, but they're essentially identical. And Voyager 1 encountered Jupiter and Saturn, and then it took it off on a trajectory out of the solar system. And Voyager 2 also undertook flybys of Uranus and Neptune. This is a diagram, a photograph of I believe it's a photograph of a model of the spacecraft, of Voyager. There's that dish that I mentioned that was one of the spares was used for Magellan. So he benefited from the overlap in time of the different missions. We see the similar sorts of bits and pieces that we were seeing way back with Mariner 2 in 1962. We have this electronics box housing all of the systems on the spacecraft. We've got this parabolic antenna to communicate with the Earth. We're starting to see some additional structures. We see these booms here to put the instruments a bit further away from the spacecraft, give it a bit more flexibility. More cameras, more types of instrumentation on board. The one thing we don't see here is we don't see solar arrays. And that's because this mission is intended to go way out in the solar system. It's intended to go right out to Neptune. where effectively sunlight is negligible. Sunlight, the power that you can extract from sunlight, I'll show you, as you all know, falls as the inverse square of the distance. So if you're generating, say, a kilowatt here from a solar array in Earth orbit, you go out to Neptune at about 5 astronomical units, and you're generating 1/25 of that. You go out to Saturn, and you're generating 100th of that, so you've only got 10 watts of power to play with. You go out to Uranus, that's at 20 astronomical units, so you're now talking about 1/400th of the power, so it falls off very quickly, and it very quickly becomes essentially negligible. So you need another power source, and that's what this thing is here. That looks a little bit like a battery, but it's a big old battery. This is, you might be able to read the label there, that says radioisotope thermoelectric generator. That's also known as an RTG, and that is the power source for the Voyager spacecraft. And I'm going to show you pictures of this same technology in operation on Cassini shortly. And basically it utilizes the energy, the heat from radioactive decay, and converts that to electricity. And it's used in most deep space missions where you're going to be far away from the sun. So that was Voyager going out into the solar system, and then as soon as we started getting the pictures back from Voyager, so I talked about how we started to see these volcanic eruptions from Io. People were saying, we've got to go back there. There's so much interesting stuff. All of these satellites are really interesting and unique. These satellites that Galileo discovered in the 1600s, they're absolutely fascinating worlds. We've got to go back. And so the response to that was Galileo, the Galileo spacecraft, launched in the late 80s, but it was actually built in the early 80s, and it was scheduled to be launched from the space shuttle. And as we all know, the Challenger disaster happened in 1986, and the shuttle fleet was grounded. They couldn't launch anything anymore, and Galileo was ready to be launched. And so what they had to do, they just had to put it in storage. And what they wanted to do with Galileo is that they wanted to get back lots and lots and lots of data. And basically, the bigger your dish, the bigger your antenna, the more data you can get back, or the faster the data rate you can get back. But there's only a finite diameter of antenna that you can fit into a launch vehicle, even with the space shuttle's cargo bay. So what they did actually with Galileo is that they said, well, let's make it folding. So let's have it all folded up like an umbrella. And then once it's in space, we'll open our brolly and make a really big antenna. So this is fine in principle, but it is a single point failure. And what had happened was that they took it out of storage once the shuttle fleet was running again. They took Galileo out of storage, but they forgot to lubricate these joints at the top. And so when Galileo was in space, and they decided, right, okay, we've got it in space now, we need to unfold this antenna. They actually found that some of these ribs of the antenna, just like the ribs on a brolly, they stuck. And so the antenna didn't deploy properly, and so they basically couldn't use it. So they had to use a smaller antenna. It's down, I know it's down here somewhere, but I can't remember which part of the spacecraft it is down here. But they had to use one of these antennas that basically sends the radio, or microwave, in this case microwave energy, in more or less all directions. And so that greatly reduces how much data you're able to get back. So it really limited Galileo. But the same story was already also unfolding with Saturn. Voyager went past Saturn, and we see all of these icy satellites. We see these fantastic rings. We're intrigued by Titan, the second largest moon in the solar system, the moon with the thickest atmosphere in the solar system, and we say we've got to go back. And so there was a process to find out, to get back to Saturn as well. And that resulted in the Cassini-Huygens mission, which is a collaboration between, or was a collaboration between NASA, the European Space Agency, who provided this lander here. So this lander here is called Huygens that landed on Titan. And also the Italian space agency, ARSI. ARSI built this high gain antenna. And again, we have got very, very similar parts. Let me just see if I've got a diagram on the next. Yes, okay. Yeah, so this is an artist's impression of Cassini entering orbit around Saturn, firing its main engines so it could be captured by Saturn's gravity. And if these are some diagrams showing Cassini being constructed, being built, we see the high gain antenna, and again, we're seeing similar elements. You know, even though this was being built in the 90s, we've still got a sort of roughly octagonal electronics box. We have got fuel tanks strapped to it. We've got these RTGs, these radioisotope thermoelectric generators that we used on Voyager. Very, very similar elements. And indeed, the platform here, the spacecraft skeleton, if you like, before you start sticking on instruments and whatnot, it was known as the Mariner Mark II platform. So we're following a heritage on even from the 60s. But this is enormous. You can see the scale here compared to the engineers, and you can see Cassini fully constructed. The Huygens probe is attached. All of this gold thermal insulation is attached, and it's been put into a vacuum chamber for testing. And so this thing is about the size of a small minibus. The high gain antenna here is 4 meters across. So I'm 1.8 meters, 6 foot. So that's about 15 foot across. This main high gain antenna here. And this insulation, this gold-looking insulation, that's not put on there to make it more expensive. It's put on there to regulate the internal temperature of the spacecraft. You've got to keep the electronics at a fairly constant temperature. You know, if they get too hot or too cold, they stop working. And so you need to regulate the temperature. But Cassini's route out to Saturn took it past Venus and then out to Saturn. And so that's a tremendous difference in energy, in heat, on the spacecraft. You know, I sometimes describe it as saying you've got to walk from the equator to the North Pole. And you can either wear a jacket or you don't wear a jacket, your choice, but you've got to stick with your initial choice. And that's how clever the insulation is, to keep it cool when it's near Venus and warm when it's out at Saturn. And then this power source, this nuclear power source. So you can see one of these RTGs being examined here with the radiation meter. And stacked inside this RTG are these pellets. And this is a pellet of plutonium dioxide, and it's red because it's red hot, not because it's been painted red. So, and it's red hot because of the radioactive decay. And so, you know, some of you probably remember Chernobyl in the 80s and how long that took to cool down. And it's the same principle here. But every time an atom in that material decays, it releases energy, which keeps the whole thing warm. And so basically what they do is they stack them up inside this device and then basically construct a thermocouple. They put a probe on the hot metal, they put a probe out to cold space, and then there's a temperature difference between those two materials, and that drives a potential difference, and you can convert that thermal energy into electrical energy. That's how Cassini is powered, and lots of other missions as well. So for example, we looked at Curiosity. We looked at the landing of Curiosity. Here is an RTG on the back of Curiosity on Mars at the moment. Here is an RTG on the surface of the moon, powering some of the lunar surface experiments. And these things are designed to be really rugged, and if a spacecraft burns up in the atmosphere, would they basically burn up and distribute plutonium through the atmosphere to rain down for us all to breathe in? Quite apart from the fact that plutonium is radioactive, it's also very poisonous. So you don't want that to happen. But there have been instances where they've re-entered, and here are 2 RTGs on the surface on the ocean floor that are still intact and are monitored to this day to make sure they're not leaching radionuclides into the environment. So they're still monitored. They don't want to pick them out because they don't want to disturb them and potentially release contamination. So they just monitor them. But it's a really useful technology for deep space exploration. I did talk to you about Enceladus before, but I wanted to show you this video again, just in case some of you may not have seen the previous talk on Enceladus. And I want to just show you all of the different operations that actually happen to a spacecraft when it's taking these scientific measurements. So what we're looking at here is we've got sort of an artisan, a rendering of the spacecraft, and this is what the instruments are looking at. And we're looking at a flyby of one of Saturn's moons. And the point here, to take away here, is that the spacecraft has to be programmed to do all of these different things. It's got to be programmed to turn around, to point different instruments at different things at different times. And so what has to happen is that in advance of a spacecraft flying past a moon, flying past a planet, whatever, basically a program has to be written, a set of instructions has to be written and sent up to the spacecraft in advance. So, someone's job to sit there and decide what the spacecraft will do at a given time, what the instruments will do at a given time, compose that into a program, and then it gets uploaded to the spacecraft. And that's a real-time process that happens all the way through a space mission. Is this thing of planning? What are we going to do next? What instruments are going to point? How close are we going to get? And that sort of thing. So there's a lot of activity goes on, engineering activity goes on after the launch. So just to finish up with a couple of things, a couple of more recent things. I'm sure most of you are aware of Rosetta and the little lander Philae that landed on Comet 67P a number of years ago. These solar arrays here are absolutely enormous. This is a spacecraft operating several AU away from the Earth, and so they needed to be so big to counteract that inverse square law with sunlight. And so even because it went out to the orbit of Jupiter, the energy it was getting from sunlight was so little that it had to go into a hibernation mode. And every so often it was just pinging the Earth saying, I'm still here and I'm still alive. And it was pre-programmed to wake up at a given time when the sunlight will be enough to power all the systems on board the spacecraft. And that little Philae probe was released and touched onto the comet, but you may know that it actually bounced off the comet, and they couldn't find it for quite some time until they actually found it in these pictures where you can see it just on its side up against a rock. And I think it's amazing to see these pictures of spacecraft on other worlds, just a little bit like seeing the Apollo landing sites on the surface of the moon in LRO images. It's quite a powerful picture of, hey, we were here, sort of thing. You may have heard about Schiaparelli, and this is part of the ExoMars program to to get Europe to land on Mars. And so Schiaparelli was a demonstrator to test the technology, and you may remember that this Schiaparelli landing was quite a spectacular failure. And they've actually found the various bits on the surface of Mars. So this is actually the impact location, where basically it slammed into Mars at basically terminal velocity and blew up. And all of these other parts, so down here we see the parachute and the rear heat shield, a little bit like we saw the heat shield falling away from Curiosity, and so on. So that actually there's the front heat shield. That's the bit that fell away, and the other part is the back part up above. Is the rear heat shield and the parachute from Schiaparelli. But it basically failed because of a software bug where it basically didn't realize it was upside down, and it thought it was upside down, so it didn't actually know what its altitude was, so it didn't know when to turn the rockets on. So again, it shows you how simple bugs can creep in and cause a failure, even though you do all of this advanced engineering and design and testing. And then getting further out into the solar system, I mentioned New Horizons earlier on, and receiving these fantastic images and fantastic data from Pluto and Charon, and going further out to Ultima Thule, seeing these objects really, really very far away in the solar system. And again, we're seeing the same sorts of elements. There's an RTG here to power New Horizons. Here is the antenna here communicating with the Earth. And even though it's got this big antenna, it's so far away from us now that the data was coming back from New Horizons at less than 1 kilobit per second. So it took months and months and months, I believe it's about 18 months, to get all of the data back to Earth from the New Horizons flyby of Pluto. That's a real challenge when you're going this far out in the solar system, is how do you get the data back? And that's an engineering challenge we're trying to solve today. And then finally, I wanted to just show you some moon landings, or a moon landing. And this is Chang'e 4, a Chinese mission that landed on the moon. And it landed on the far side of the moon at the South Pole. It carried this experiment to grow seeds on the moon. That was a partial success. But the thing I want to show you is a video of the landing. And I'll get this up and I'll play it and I'll talk you through the landing. And this is an example of a spacecraft trying to do collision avoidance. It's trying to land on the moon autonomously, but also looking out for stuff that might get in the way. So, I'm sure you've all heard the story of Armstrong and Aldrin landing on the moon, where Aldrin had to take control because they were about to hit a boulder. And it's a little bit like this with these spacecraft. So you see the spacecraft coming in, and you see it start pitching over. And as it pitches over, you see it pitching over there and saying, well, can I land on that or can't I land on that? And it's, if you've got a phone that's when you try and take a picture, it tells you what you're taking a picture of. So sometimes I'll get my phone out and I'll try and take a picture of my cat, and it will put a box around it and it will say cat. So it's doing the same sort of thing, but it's actually looking for things it might collide with and actively trying to avoid it. So you'll see it now, it's scanning around, it's trying to make a decision. And this is part of a little bit like the technology on Mariner 2. It's trying to keep itself safe. It's trying to make decisions just with technology that's decades further along. So I think it's quite amazing to see these machines making these decisions, these robots making these decisions. So I hope you enjoyed that. I'm going to leave that there. Thank you very much for listening. I'm very happy to answer any questions you've got. I hope the connection worked out well. Thank you very much for having me.
Thank you, Chris, for an excellent talk. Could I ask you to stop sharing your screen, please? Question time. That was an excellent talk. Thank you very much, Chris. Just on a question from me first about the point at which a spacecraft design is fixed. You've been involved in several missions now. Did you have any input into the design of the instruments? You need to unmute yourself, Chris.
I didn't have anything to do with the instruments on Cassini, but I have had some input on some of the instruments on JUICE. To the best of my knowledge, they need to be fixed relatively. They need to be frozen relatively early, because you've got to build all sorts of. You build multiple copies. You need to build a flight instrument. You need to build an identical copy that's a flight spare. You need to build engineering models that you sort of almost like test to destruction. So obviously you can make small changes there, but these things all propagate through. So even relatively small changes can have consequences for the mass of the instrument, for how the spacecraft balanced, So there are lots and lots of knock-on effects where they need to be frozen relatively early in order to not have knock-on effects later down the chain.
So just thinking about the timeline between the design being frozen and the mission being launched, never mind about the time for the space flight and the actual science mission to start. What's the time between freezing and mission launch typically, or in the case of JUICE, if you can't be?
I would say several years.
Right.
Several years. And the designs have been, the designs for some of the instruments on JUICE have been frozen for several years. The
I'm going to push you on this point a little bit, because several,
yeah,
it's a blanket term. And
yeah, well, I'm being deliberately vague because I don't have a specific number to.
Yeah, are we talking about 2 or 3, or are we talking 5, 6?
I would have said in some cases 5 or 6. Right. If it has the potential to have a big effect on the spacecraft, or not, and risking a launch date, then then you would have to be talking something more like 5.
Right. The reason I'm asking is that people often ask, why are the rates so slow? Because technology on the Earth has moved on so quickly. And people ask the question, well, why did they choose such old technology? But you've answered that. Thank you very much. Ladies and gentlemen, it's over to you. Once again, I have got 30 odd people to look at. So if you want to ask a question, put a hand up. I prefer a digital hand. Wave at me, but give me time to scan through everybody's image. Roy Wayne, sorry, Roy, I was pulling somebody's name out of the back of my head there. Roy Dunson's got a question. Can you unmute yourself, Roy?
What I was wondering, Chris, is that if you were in charge of NASA, is there a particular object in the solar system that you would send a probe to personally?
Well, I'm biased. I would go to Uranus or Neptune, but I am a little biased. And I say Uranus and Neptune because we've only had one encounter with them. It's only we were last at Venus in 1989. We were last at Uranus in 1986, and there are so many things we don't understand. Because of the time Voyager 2 arrived at Uranus, we don't even know what's on the other side of the moons. We only saw the southern hemisphere of the moons. We don't know what's on them. There could be civilizations. There could be monoliths. We just don't know. So for me, they're really compelling and interesting places to go to.
You'd need 2 missions.
Yeah, you kind of need 2 missions. Well, one would do, either Uranus or Neptune. I prefer Uranus, but again, that's my bias.
Okay, okay, Roy. Anybody else? Looking around, I think you've bamboozled everybody. Whilst we're waiting for people to pick up courage, they're very quiet tonight. I don't know what you've done to them.
Catherine has raised her hand.
Oh, has Catherine raised it? Oh, sorry.
Oh yes, I always ask questions. People are working more on doing ion drive. Does this mean that we can send out missions to the far planets like Uranus and Neptune far quicker now?
Usually, ion drives are included in a lot of mission designs now when you're going out that far, and the advantage of it is that you just get this soft, gentle push that you don't. It's not brutal like you fly off as fast as you possibly can, or you get out into space and you do big brutal chemical burns. Yeah. You can really sort of go out in a softly and just have a push for a long time. The disadvantage with it is that you need a good electrical power source to run it, and there you're talking about kilowatts of electrical power. so that if you're using a solar array for that, that's really good close to the sun, but eventually you fall to this 1/r² curse, and eventually
Yes, yeah.
it stops being efficient. And so what they tend to do is a bit of a hybrid approach of saying, well, we will use these ion drives closer to the sun, and then the spacecraft will be composed of 2 stages, and you'll separate off the ion stage, and that just goes off as debris, and what's left behind is the thing that will actually go on a free trajectory out to Uranus. It's got a chemical engine on, so it might do some mid-course corrections. It might do a gravity assist with another planet, and obviously you've got the chemical engine to enter orbit once you get there. But certainly ion drives, you know, I'm not aware of a mission designed to, well, I'm aware of one, but usually they nearly always use some form of ion drive because it's efficient. Good question.
Okay, Catherine.
Thank you.
I'm not seeing anybody else. I do have another question, and I just want to bring up the subject of the morality of actually sending a dirty instrument built on Earth and dropping it onto on a virgin moon, on a clean moon. And however good we think our clean rooms are, they are not 110% clean.
Absolutely right. Yes.
Do we really have that right to do that?
Oh, lovely. So I will answer it technically, and I'll maybe offer some of my thoughts about the morality. So the technical aspect is, yes, they are constructed in real clean rooms. There are different standards depending on what planet you're going to, what body you're going to. So the stringency of cleanliness if you're going to Mars is much, much higher than if you're dropping a probe into Jupiter or you're going to Venus. And it's about the chance that there will be extant life there that's not from Earth. So they are built in extremely clean. So let's take the thing of Mars. You're building something in an extremely clean room on Earth, but then the other thing that you also rely on is the instrument and the spacecraft being sterilized during the interplanetary flight out. You know, so in that 9-month period when you're going from Earth to Mars, you rely on the fact that the spacecraft is being bathed in cosmic rays, it's being bathed in radiation from the sun, and that will perform additional sterilization of both the external and the internal surfaces of the instruments. So that is an additional part of the cleanliness. The problem with that is that if you want to go and land on Europa, for example, and you want to go and go through the ice and enter that subsurface ocean, is that the environment, the radiation environment at Jupiter is so intense that you need to design your instrument so that the internal surfaces are not available to be irradiated. So it makes it extremely expensive to construct the instruments. You have to get into sort of very detailed heat treatments, chemical treatments. You're sort of talking, you know, crudely speaking, about bathing these things in bleach before you can put them on the spacecraft. So it becomes extremely expensive to do it properly. So that's the sort of the technical side. So I think it's fair to say it's less of a problem when you're going into a less radiation intensive environment, but if you're going into a radiation intensive environment, you basically need to shield the whole thing so it doesn't get fried before you can even do the science. Now the morality side, the morality aspect is really interesting. I think you're absolutely right that there's a question there about we've roughshod over this entire planet, and then let's go and do it elsewhere. We've got nowhere else to destroy, so let's go and destroy somewhere else. I think some people would say that, I think some people would just respond to that moral argument by saying it's basically already happened anyway, because of, because of rocks being knocked off the Earth and things like that, that our DNA is probably, or material from Earth has probably been spread across the solar system anyway. I think there's an allied aspect there of, part of this planetary protection is to say, if we go to Mars and we find little green men, are they actual Martians, or have we taken them there? So if you find a bacterium on Mars, did we take it there, and can you be sure that we didn't take it there? So I think that's a related aspect, but more about the science. But the moral question is really intriguing. I worry less about that on Mars, because it's an inhospitable environment anyway. I have more concerns about that with these subsurface oceans at Europa and Enceladus and Titan, where we know they're liquid. Therefore, we know that they must have some heat source there. So we come back to those whole black smokers. So I'm more worried about the morality of it at a body like Enceladus and Titan and Europa. It's a tricky one. I do think that it's part of the human condition to go and explore, but I guess in this moment I'm trying to balance that against not doing what we've done to this planet.
Yeah.
And you could have a very pure aspect of, we're going to explore and we're not going to destroy, but that doesn't mean to say that the next person won't go and destroy.
I think I concur with your last point about it being part of the human condition to explore, and it's such a drive in human beings to go and see what's over the next ridge, what's around the next bend in the river, that we will go there with the best of intentions. But we know what humans do when they do things with the best of intentions.
Yes, absolutely. Yeah, absolutely.
Let's get back onto a lighter note. I'm still questions, and they're very quiet tonight. I think.
If people are thinking about some questions, I can expand a little bit on what you were talking about earlier about the data rates, and basically that just comes down to a balance between how much electrical power you have to power a transmitter and how big you can make the antenna. There's an effect on the wavelength of the electromagnetic radiation you use, and so you can go to, if you use lasers, you can get a higher data rate, but it's relatively new technology and it's only been tested in space a few times. And I think there's a reticence there to make another single point failure, like with Galileo.
Yeah. Okay, Catherine's got another question.
Yes. How far off is sending a probe to land on Europa?
How far away?
Yes. Presumably there must be proposals for it.
There are proposals for it. We've done this at Titan. We've landed on Titan. There the challenge is that there it's a little bit easier because it's a thick atmosphere, so you can use parachutes and the like. At Europa, there's another challenge of being able to slow yourself down.
Your cat has turned your microphone off, Chris.
I will let her out. I'm amazed that she stayed that quiet through this whole talk. Yes, you've got the problem of landing on Mars. What technology do you use? You get out to Jupiter, you get around Europa, and then how do you get down to land? So you need some rocket technology to get down, once you've got down onto the surface, what do you do? And there's a question there about how much actually useful stuff can you do. You're basically just putting a webcam on the surface, or are you actually doing something where you're going to take some samples? You might scoop up some of the ice and do some chemical analysis on board. What can you actually achieve when you're on the surface? So I actually think all of the technological pieces are basically there. We've got all of the technological elements. We know how to land on planetary bodies. We know how to get there. We know how to build the instrumentation. There's a real question there of cost. And people have been, NASA has got this mission called Europa Clipper, and people were talking about landers as part of that, but it got de-scoped because the whole thing got so expensive. And part of that is this cleanliness aspect, and part of it is just that people want a Christmas tree. People want to send everything in the kitchen sink to the surface. So it's difficult with the JUICE mission to Jupiter and Ganymede. For a while, there was a discussion there about the Russians providing a lander to go and set down on Ganymede. So in fact, that's an interesting point, that JUICE is actually the end of mission for JUICE is actually going to be a controlled descent to touch down on the surface of Ganymede, as gentle as they possibly can. So we will have a piece of human engineering on Ganymede in the next couple of decades. But like I said, I think the technological pieces are there. It requires the finance, I think, because it is expensive, and you've got to cast that against what else can we do with this money.
Okay, Catherine. Okay, just one last question from me then, Chris. And so, which do you consider the harder? Counselling human beings or interplanetary robotic missions?
This is a very interesting question. It's a very prescient question, because we were talking about that. I was thinking about this morning. We were having a conversation at work in one of our regular meetings. We were talking about analysing some data from Cassini. We were actually looking at some data from Cassini and trying to examine what was real, what was an artifact, what was an effect of just the finite resolution of the instrument, that we couldn't measure anything smaller. And I sort of was I quite like that facet of the work of of trying to squeeze the best out of the instrument that you possibly can. How can we extract the most information out of this data set that we've got from this alien world? And so I sort of came off that meeting thinking about this, and thinking that there's so much in these instruments and so many things to understand with these instruments. And I sort of contrasted that against counselling training, and thinking, well, actually the instrument is you. And the training there is all about, being more in tune with your instrument, with being in tune with yourself. So it's a bit more subjective and a bit tougher, and the instrument tends to behave more normally and regularly in unexpected ways. So I don't think I've really answered given you a which way or the other, but it's interesting. There are some interesting textures to it.
Right, thank you for that. I think you find the interplanetary easier, actually, from your answer. Chris, thank you very much. Just leaves me to say you're always welcome to come and talk to us, and hopefully next time we'll be able to buy you a pint of beer as well.
That would be smashing. I would look forward to that.
Can we give Chris Aldridge a big Mexborough and Swinton Astronomical Society? Thank you. Thank you very much, Chris.
Thank you very much for having me.